Here we have a simple page of notes, and it's going to describe how resistors behave when we put them in series. We kind of already know the answer to this based on our Kirchhoff loop, but let's take a look at what's here. The top part of the page has some diagrams right out of your book, and the way they describe the resistance in series in the textbook is by looking at the battery EMF here with an internal resistance. So they bring the internal resistance back in, the little r. So we have our EMF here. We have the positive terminal voltage of the battery here. We have 0 volts, our negative battery here. So they include both R's, and the two resistors in series then are little r and our load resistor, capital R. And they look at a current I going through the circuit. So it's current I going through the battery, through the little r, and through the load resistor. Well, the example numbers I used here, let's pretend it's a 10 volt EMF. So the EMF, for example, I said was 10 volts here. And let's say it's a 1 amp current. If the little r is 3 ohms and the big R is 7 ohms, then what we get is V equals IR. We get a 3 volt voltage drop across the internal resistance, so we lose 3 of the 10 volts due to heat, and then we take the other 7 volts and drop it across the load resistor for our usage. Now, for the bottom part of the page where I have the derivation of our resistors in series, I want you to make a note that for the bottom part of the page here, I have let the internal resistance, little r, go to 0, so no internal resistance for the bottom part of the page. And what I did was I added a capital R1 in here. I made the load resistor now R2 for the bottom part of our discussion, and I added an R3. All of them in series, so the same current is flowing through R1, R2, and R3. And since we now know our Kirchhoff voltage loop analysis, let's do it. Let's throw a Kirchhoff voltage loop in here. And look at the loop equation. Sum of the voltage sources equals sum of the voltage drops. Well, our voltage source with no internal resistance is just our terminal voltage. Sum of the voltage drops are all the IRs that we did with our Kirchhoff voltage loop. The loop and the currents all go in the same direction, so they are positive IRs. And we can see that if we were going to replace all those resistors with a equivalent or total resistance, the same I would flow through everything. I's cancel out, and voila, we get that the equivalent resistance, R123, I'll often use R total is R equivalent equals sometimes R123 when I do the homework problems equals R1 plus R2 plus R3. They add. So resistors in series add. This is the inverse of what we saw with capacitors. Capacitors in series added reciprocally, so as long as you memorize one or the other and just know they behave reciprocally, then it's not a bad way to remember them. I tend to remember the resistance one, believe it or not. Resistors in series add. Also very important to know that the resistors in series divide up the voltage. So whatever the total voltage is, it acts as a voltage divider circuit when you put resistors in series. And the last thing I have here to show you is that kind of makes sense even based on making a longer wire. So we increase the resistance by making a longer wire. And really, when we put the resistors in series, we're just making a longer or bigger resistor, making the bigger R. So there we have it. That is our resistors in series. Most important thing is to have this equation memorized and be able to just use it very quickly when we do our analysis.